Section 6-4 is on the number e, exponential functions, and logarithmic differentiation. And the objective of this section is to use logarithms to differentiate exponential functions. And the idea of using logarithmic differentiation, which is what we're going to focus on here, is to simplify the problem first before you go through and find a derivative. And you've seen techniques that we use kind of like this to some extent with other problems. You've seen with in the first half of this section, in fact, where we use the composition of a logarithm and exponential function to eliminate those two or simplify the problem first before you find the derivative. And we've done that for a number of problems that we've used either properties of logs or whatever properties we could along the way to rewrite the problem, get it in another form, and then take the derivative of that. And the same is true with antiderivatives too. We've used a technique, I guess the one technique you've seen is variable substitution or U substitution. The whole idea behind that is to simplify the problem so that the antiderivative is much easier to find. And that's what logarithmic differentiation is all about. Simplify the problem as much as you can so that the derivative becomes easier to find. All right? So let's take a look at what the technique actually is here. Logarithmic differentiation. There's basically 3 steps here that we're going to go through to be able to use this technique. And so let's just write down what those steps are here. So the first step is to take the log of both sides of the equation. Well, regardless of whether the problem involves logs or not, we're going to take the log of both sides. And the reason for doing that is because we can then use some properties of logs to help us simplify the problem. And in some cases, that's all we're doing. And in other cases, as we'll see, this is the only technique we'll have in order to find the derivative of that particular function. The second step is to use implicit differentiation to find the derivative of the logarithmic equation. The reason why we have to use implicit differentiation is because, of course, when you take the log of both sides, it's not going to be solved for y anymore. It's not an equation solved for y, which means that you have what's called an implicit relationship or an implicit equation there, so therefore the derivative is going to be an implicit derivative. And then the last step is to solve for y prime in terms of x. And you've seen that many times now with implicit differentiation, that you end up with y primes kind of scattered all over the place. Now in these problems, for the most part, you're going to find there's one y prime, and it's on the one side there where y was, of course. And you can relatively easily solve for y prime. It won't quite involve as many steps. All right, so let's try a couple of examples. Take a look at example 3 here. Example 3 says to find f prime of x, and they tell you that f of x is equal to x cubed plus 4 raised to the cosine of x. Now we've talked many times that when you go to find a derivative, the first thing you got to figure out is what type of equation are you looking at here. Is it a product? Is it a quotient? Is it a composition, etc.? All right. So when you look at this, this definitely looks like a composition because I have an inside function. That's the what we call the base of this thing, the x cubed plus 4. And you also have an outside function there, which is the cosine of x. The problem that we have here is that the outside function is not just x, or excuse me, it's not just a number. It's not just a constant. It's a variable. So with that understanding that if the exponent is the variable, that means we must be looking at an exponential function. However, if you look a little closer and look at the base, now the base has an x in it as well. It's x cubed plus 4, which if the x is in the base, then we say that this must be a power function. So we got two things going on here. One part of it, the base, says it's a power function. The other part of it, the exponent, says it's an exponential function. It's a combination, if you will, of those two. We don't have a rule of how to find the derivative of a combination of an exponential and power function like this. All right? So I need another technique. So the technique that we're going to use is the technique we just talked about, logarithmic differentiation. So we're going to start out by taking the log of both sides, and in this case, in fact, for all of these, we're going to want to use natural log. So we're going to take the natural log of f of x, and set that equal to the natural log of x cubed plus 4 raised to the cosine of x. This is an example, by the way, of a function where the only technique you're going to have in order to find the derivative of this is with logarithmic differentiation. And the whole reason is because you've got an x in the base and an x in the exponent. Now, the reason for doing this is because we have a property for logs that says if you have a log of a power, which is kind of what we've got here, x cubed plus 4 raised to the cosine of x, that you can bring that exponent out front. Okay? So let's use that property. So this becomes the natural log of f of x is equal to the cosine of x times the natural log of x cubed plus 4. And now if you look at what you've got, on the left side here I've got a composition of a natural log and f of x. Those are both things I know how to find the derivative of. On the right side, I've got a product of cosine and natural log of actually a composition over there. Those are all things I know how to find the derivative of. I no longer have this form where I had an x in the base and an x in the exponent there, and thus had a problem of figuring out how to find the derivative of it. So now we're ready to take the derivative of this thing with respect to x. All right, go ahead and write that out front here, that we're going to take the derivative of this with respect to x. All right. So to do that, on the left side there, use your rule for the derivative of a composition. The rule is it's 1 over the something. That's the derivative of a natural log function. And then chain rule says you substitute in the inside function. And then the last part of chain rule says you multiply by the derivative of the inside function, which would be f prime of x. And realize that's what we're trying to find. I want to find out what f prime of x is equal to. On the right side of this, we've got a product, so follow product rule. So the derivative of the first function, derivative of cosine, is a negative sign times the second function, natural log of x cubed plus 4. And then we add to that the first function, that's the cosine of x, times the derivative of the second function. Now there's a composition again, so follow chain rule as we do this. It's 1 over something, and then chain rule says you substitute in the inside function, x cubed plus 4. And then multiply by the derivative of the inside, which is going to be 3x squared. All right, and our goal here again is to solve for f prime of x. So we're looking for this guy right here by himself. So let's take the f of x and move him to the other side. The 1 over f of x, if I multiply both sides by f of x, I'll end up with just f prime of x over here on the left side. And then I'll have f of x times all of this stuff that I have here. If there's any simplification here, we could do that while we go through here, but the first part of this looks pretty much the same way. Negative sign of x, natural log of x cubed plus 4. And I guess I could rewrite this as, let's go ahead and just write it as a quotient here, as 3x squared cosine of x in the numerator over x cubed plus 4 in the denominator. And the last step of this is to replace f of x with what it's equal to. F of x, we started out by saying f of x was this x cubed plus 4 to the cosine of x. So let's substitute that in. This is x cubed plus 4 to the cosine of x times negative sign of x times natural log of x cubed plus 4 plus 3x squared cosine of x divided by x cubed plus 4. There is our derivative. That's what our goal was there. Find the derivative of that function. All right, let's take a look at one more example. So again, here's an example that we just saw here for example 3. The only method you have is logarithmic differentiation. Have to use that technique and then use implicit differentiation. Let's take a look at another example. Here's an example where we could take the derivative as is. However, if you'll see that if we use logarithmic differentiation, we can kind of simplify this a little bit. So here they give us f of x is equal to 3x squared, or excuse me, 3x plus 7 to the 5th. Yeah, to the 5th. I said squared and then I wrote it. To the 5th divided by the cubed root of x plus 2. Now, if you took the derivative of this thing just as is, realize you've got a quotient here, so you got to follow quotient rule. But then on top of it, the numerator is a composition, so you have to follow chain rule there when we take that derivative, and the same is true in the denominator. So it'd be a little bit of work to do take the derivative of this, but we certainly could. Instead, let me show you another technique that we could use. Let's use logarithmic differentiation. So we're going to take the natural log of both sides. Natural log of f of x is equal to the natural log of this whole thing here, 3x plus 7 to the 5th power, divided by the cubed root of x plus 2. All right, now the reason for doing this is over on the right-hand side, I have some properties of logs that allow me to simplify this. So the left-hand side, let's stay the same, and the right-hand side is what I want to rewrite. If I have the log of a quotient, which is what I've got here, I can rewrite that as the difference of logs. So I can rewrite this as the natural log of 3x plus 7 to the 5th power minus the natural log. Now, I'm going to rewrite this as a power here again because that's what I want to eventually have this as, but the cubed root of x plus 2 is the same as x plus 2 to the 1/3 power. So that's how I'm going to write it, x plus 2 to the 1/3 power. And even in this form, that wouldn't be too bad to work with, but however, I have a property here that says that if I've got the log of a power, I can bring that exponent out front. I've got that twice here. I'm going to use that property first. So it's the natural log of f of x on the left side, and I get 5 natural log of 3x plus 7 minus the natural, minus 1/3. Forgot my 1/3 there. Minus 1/3 the natural log of x plus 2. Now again, as you get going with these, you're going to be able to probably quickly write these down in this form. You don't necessarily have to show all the steps like I did to get to this point. But certainly as you get started with it, you might want to write down several steps there so you don't get the wrong equation, obviously, here. But there's the result after our taking the log of both sides and using our properties of logs. And now after this, we are all set to take the derivative of both sides of this using implicit differentiation. So we end up with 1 over f of x times f prime of x. That's using chain rule, of course. And that's equal to 5 times the derivative of natural log of 3x plus 7 is 1 over 3x plus 7. Just follow chain rule again. Times the derivative of the inside is 3. And then minus 1/3 times 1 over x plus 2 times the derivative of x plus 2, of course, is 1. And now let's move the f of x to the other side. So we have f prime of x left on the left side. And that's equal to, move that up there, f of x times this whole quantity. Let's multiply the 5 and the 3 together to get 15 over 3x plus 7 minus 3 over x plus 2. And you do not need to worry about getting a common denominator there and combining those two. You certainly could if you wanted to, but I would not worry about that. The last step then is to replace f of x with what it's equal to. Now again, f of x in this problem was this quotient here, 3x plus 7 to the 5th over the cubed root of x plus 2. So it's 3x plus 7 to the 5th over the cubed root of x plus 2 times 15 over 3x plus 7 minus 3 over x plus 2. And there's our derivative. Okay? Now you can decide, like I said, on this problem here, it's up to you whether you prefer using quotient rule followed by chain rule a couple times. Certainly would give you the correct result. You would probably get an answer in a different form than what we have here. Actually, you definitely would. However, the answers would be equivalent. If you were to graph the two, you could see that you get the exact same graph. But there is the logarithmic differentiation. And you'll get a chance to work on that in your assignment.